Good morning and welcome to this postgraduate video course on advanced hydrology. Today we will start the 21st lecture in this course. Before that, we would like to as usual go back and look at what we did in the last lecture. In the previous class, we completed the development of an algorithm for estimating the abstractions from precipitation using Green-Amt equations. All right, we said that we would develop this algorithm for Green-Amt equations, but any other infiltration equation can also be used. While developing this algorithm, we marched in time domain, in which we said that we can analyze each and every time step, compare the relative magnitudes of the infiltration rate and the intensity of rainfall, all right, at the beginning and at the end of a time step. All right. Then what we said is we can characterize each and every time step into one of the three possible ponding cases, and depending upon that we can use the appropriate equations to calculate the infiltration at the end of the time interval, and once we have that, we can calculate the effective rainfall heatograph. Then we moved on to a new method which is called the SCS, or the soil conservation service method, which is applicable for storm rainfall. We can calculate the effective rainfall using this SCS method, all right, in terms of a parameter which we need to estimate, which is called the curve number. And the SCS has provided tables depending upon the soil type and the land use, land cover conditions, and it gives us the curve number. Okay, and this curve number is given for the normal antecedent moisture conditions or the initial conditions. They have also given us the equations to estimate the curve number if the initial conditions are on the drier side or on the wetter side. After that, we started developing the model, the rainfall runoff model for the surface flow or the overland flow. We looked at the schematic diagram and we defined the various variables, and we said that our objective is to calculate the flow depth and velocity at the outlet, all right, at the end of the overland flow. Okay. What I would like to be able to do next is take the continuity equation where we stopped in the last class. Okay. So, what we are looking at is the expression for flow depth and velocity for surface water. Okay. We will analyze the surface water first as the overland flow and then later on as the channel flow. We have already written down various variables that are involved and the control volume. Okay. And then we said that we would write the continuity and momentum equations for the control volume which we have considered in this particular case. What are the inputs and outputs? Well, the rainfall is falling from the top, there is infiltration taking place and there is overland flow, the flow depth is y and the velocity is v. Our objective is to find this v and y at the end of this control volume. Okay. And then we write first the continuity equation, and we state conditions. The Reynolds transport theorem for the mass comes out as this: beta rho v dot dA. Beta is 1, rho will come out, you have v dot dA is equal to 0, this is your 561. Okay. Now, with reference to the figure which we have drawn yesterday, so basically what is this whole thing? This is representing, if you look at physically what it represents is it's the second term on the right hand sides of your Reynolds transport theorem, which represents the net outflux of the extensive property flowing across the control surface, and the extensive property here is the mass. Okay. We have taken the density of the water outside, all right, which has cancelled out. So, instead of mass we can consider the volume, all right. So, net volumetric flux flowing across the control surfaces is equal to 0. Okay. So, if we apply that, then all we need to do is we look at the control surfaces, all right. what is the movement of water across that control surface, and then we just take inflows as negative, outflows as positive, sum them up and equate it to 0. What is the inflow? The only inflow is in the form of I, all right. And if we take the inflow perpendicular to your cross section or the control surface, it will be L0 cos theta with reference to the figure we have, and then multiplied by 1, which I am not writing here. Similarly, your outflow would be what? There is infiltration going out of the control volume across the same length. L0 is the length of the overland flow, which we have defined. Is there any other outflow? Yes. Okay. The other outflow is your water flowing as the surface flow across the control surface at the outlet of depth y, all right, and the volumetric flux of that would be V times y, all right. So, it will be the discharge intensity per unit of length of the overland flow. Okay. So, therefore, your this term we can write as outflows as positive. So, we add them up, and inflow as negative. So, we put a negative sign in front and then we equate it to 0, all right. Then we say that the discharge intensity coming out is nothing but V times y would be equal to, after you simplify this, I minus f L0 cos theta. Okay. So, this is your continuity equation, and I am going to number this as 5.6.2. Okay. So, this gives you, this equation gives you the Q0, which is the discharge intensity coming out of that sheet flow or the overland flow. Okay. Again, our objective is to find V and y. This equation gives you V y, all right, which is the multiplication of these two quantities. So, we need one more equation. We need one more equation to calculate both V and y, all right. So, we take help from the momentum equation, all right. So, let us look at the momentum equation. We have seen earlier that whenever we are applying the momentum equation, either it is the channel flow or it is the groundwater flow, it is in some form of equation, the famous equation we have seen. For the channel flow, it was Q is equal to KSF, or let me write it. For channel flow, initially we had written Q is equal to KSF, right. Most of you may remember that. For the groundwater flow, we had said that the Darcy's law, V is equal to Ki, represents the momentum equation. Now, in this particular case, we have the sheet flow or the overland flow, which is uniform in nature. So, for the uniform laminar flow, let us assume that the sheet flow is laminar for right now, and for the turbulent case, we will consider it later. Okay. So, for the uniform laminar overland flow, okay, what we will do is we will take the momentum equation from the knowledge of our fluid mechanics. We will not go into the derivation of that. It can be shown, all right. So, we are not going to show it here, but we will take it that the velocity is given by this expression, which is g times S0 y squared divided by 3 times of your mu. Okay. So, this represents the momentum equation for the flow conditions which we are considering. Okay. What is S naught? S naught is the bed slope, which is equal to the friction slope for the uniform flow, as you know, and this is equal to HF by L. We have seen that earlier in the first few chapters. Okay. Now, what we will do is we will try to deduce this momentum equation, all right, in a form which is similar to some other equation we have seen earlier in our undergraduate classes. Okay. So, that we are trying to analyze this flow condition all right, with another flow situation which we have analyzed already, so that we can write that equation easily. Okay. So, it will involve some mathematical or algebraic manipulations essentially. Okay. So, with this we say that the velocity then will be equal to g times hf by L. If you go back, all we are doing is I am trying to write down this equation in which S naught is hf by L, that is what we are writing. Okay. So, we are slightly rearranging this. So, you have g times hf by L times y squared over 3 mu. Okay. That would imply your hf, which is the head loss quantity, is nothing but 3 mu over y times L over y times v over g. Okay. You can see that we can come from here to here very easily. Now, what I do is I multiply and divide. Okay. I can multiply by a constant or one quantity in both numerator and denominator of an equation, right. So, what I do is I multiply and divide this equation by 8 v. Okay. If I did that, you would see that hf would be equal to it will be 24 nu over v times y. Okay. This I collect together, then L over 4 y. All right. You have multiplied by 8 in the numerator, you are multiplying by 8 in the denominator. So, 4 is here and then there is a, so it is v squared over 2g. Okay. Let us say this is 564. Okay. This equation 5.6.4, all right. Does this sound familiar to you? Have you seen an equation similar to this earlier somewhere in your undergraduate classes? Pipe flow? Yes, this is what is called the famous Darcy-Weisbach's equation, okay, in which let me first write it, which is similar to or in the form of what is called the Darcy-Weisbach's flow resistance formula in the pipe flow equation, all right, with R is equal to y. Okay. What is that? That is nothing but your hf is equal to FL v squared over 2 g d, and d here is 4 r or 4 y. Okay. So, if you compare this equation, and let me number this as 565. If you compare 565 with 564, they have similar forms. hf is equal to, this whole thing is, let us say, f L v square over 2 g, and d is 4 y or 4 r. Okay. All right, where your f is the friction factor, all right, or the friction resistive forces which oppose the motion of the fluid, is 24 nu over v times y, okay, which we can say is, you again do some mathematical manipulations, multiplied by 4 divided by 4 v r over nu. Okay. Slight modifications. Then this is, as you know, what is the term in the denominator? Do you recognize this? This is a non-dimensional number, all right, Reynolds number. Okay. All right. So, this is 96 over R e, okay, where your R e is equal to 4 v r over nu, okay, with r is equal to y we have already said. Okay. So, this equation which we see here is something like the flow resistance formula, okay, in which the head loss can be calculated using a Darcy-Weisbach's equation, which is FLV square over 2 GD. Okay. This flow conditions will be in the laminar region, all right. There is a certain condition in terms of the Reynolds number, we all know that. Okay. So, this will be laminar flow if the Reynolds number is less than or equal to 2000. Okay. All right. So, now moving on, what I am going to write is from equation 5.6.5. Okay. What I can do is I can write the equation for y as this, f v squared over 8 g s naught. Okay. I would like you to be able to see this. This is 5, 6 and 7, right. I have skipped one equation which is not very important at this point of time. Okay. So, from 5.6.5 we are trying to find out what will be y, okay, where r is equal to y. Okay. So, this is what we are doing is we are using r is equal to y is 1 and then s naught is equal to h f by l. You are using these two basic relations to come from 5.6.5 to 5.6.7. Okay. So, that is your flow depth at the end in terms of the velocity. Okay. Now, what you can do is from your original equation, you know that q 0 is equal to v times y, v squared is equal to q 0 squared over y squared. Okay. Put this in your 5, 6, 7. Okay. So, that what we are doing is we are eliminating the velocity v, so that we can get the expression for flow depth, and once we have that we can find out the other one using q is equal to v y. Okay. All right. So, it should be easy to see that your y would be equal to f q 0 squared over 8 g s naught, this whole raised to the power 1/3. Okay. So, you see that we calculate the flow depth using this equation 5.6.8 in terms of f is the friction factor. All right, we can find it out using our standard knowledge about the surface condition of the overland flow. Q naught is something which we have already written the continuity equation in terms of I minus f L 0 cos theta, that expression, and all other things are known, the bed slope and g and so on. So, we can calculate y. Once we have the flow depth, we can calculate velocity from q 0 is equal to v times y. Okay. Now, this is for laminar flow. Okay. So, this is assuming the sheet flow or the overland flow during the rainfall runoff process is laminar. What happens when the velocities increase, the overland flow or the steepness of the overland topography may be very steep. So, if that is the case, then the velocities will be high and the laminar conditions will change into turbulent. Okay. So, in that case we will have to analyze it slightly differently. So, what we will do is we will develop an expression which is most general, all right, in which we can utilize this under certain condition as the laminar flow condition and some other condition as the turbulent flow condition. So, the next thing we are going to look at is the expression for laminar and turbulent, same expression, the general expression, sheet flow. Okay. The equation which we have derived so far, or let me write it down, it is 5.6.8, is valid for laminar flow only. When the Reynolds number is less than 2000. Okay. For turbulent flow, which equation is the most important? We saw that in the laminar flow we used an expression which is similar to the Darcy-Weisbach's equation, all right, in the pipe flow. Okay. For the turbulent flow in the channel, okay, what is the most important equation? All right. For turbulent flow we use the Mannix equation. All right. So, in this case, when the velocities in the overland flow become significantly high, the Mannix equation becomes applicable. So, what we will do is will analyze this flow resistance equation or the velocity we can find using Mannix formula. All right. What is Mannix formula? This is V is equal to 1.49 over N. N is the roughness coefficient, as you know. R is the hydraulic depth, A by P times S to the power half. Okay. And this I am writing in the FPS system, okay, as per the book, and then we can generalize this for SI or the FPS system later. Okay. All right. So, if you put R is equal to Y in this equation and SF is equal to SO, all right, then what you will have is Q0 is equal to V times Y. So, if you use all of these equations into your Mannix equation, you can derive this like this. Okay. It's again I am not going to do this, but you can easily verify once you utilize all these equations or relations. What you will have is the flow depth like this whole raised to the power 3 by 5. Okay. All right. So, you see that this is for turbulent flow. Is there a similarity between this equation for the turbulent flow you had just derived and this equation? They have very similar forms. You see that Y is equal to, in the laminar case you have F, which is the friction factor. Here you have N, which is the roughness coefficient. All right, and then you have Q0. All right, here it is square, here it is linear, and then you have some other quantities in the denominator. All right. So, what we can do is we can write this expression in a very general form. Okay. Okay, as Y is equal to alpha Q0 to the power m. Okay. So, this is the general equation we can write for the flow depth, all right, where alpha and m will have different value for laminar and turbulent flow components. All right. So, let me give you these without actually deriving all this, it should be easy to see. So, for case 1, which is the laminar flow, all right, you would see that we have already derived this. Alpha will be equal to F over 8 G S naught, all of this raised to the power 1 by 3, and m is the exponent, which is equal to 2 by 3. Okay. Let me go back and see. This is your laminar flow. All right. So, alpha is F over 8 G S 0 raised to the power 1 by 3 and Q 0 raised to the power 2 by 3. So, m is 2 by 3. Okay. And case 2, for the turbulent overland flow, you would have alpha is equal to n over 1.49 under root s, all of this raised to the power 3 by 5, and m is equal to also 3 by 5. This is true for the FPS system. Okay. Remember, in the FPS system, in the Mannix equation, you have 1.49, that factor which converts your units. All right. In the SI system, we do not have that factor of 1.49. All right. So, we can write the alpha and m for SI system as well. All right, and I will give it to you directly. So, you will have alpha is equal to n to the power 0.6 divided by S 0 to the power 0.3 for the SI units. All right, that is alpha, and of course, m remains the same, which is the exponent, which is 3 by 5. All right. So, you see that this way what we have done is we have taken a control volume approach of the overland flow in which the rain is falling, infiltration is taking place and the overland flow or the surface flow is taking place. With that we applied the continuity equation and the momentum equation, then we combine the two to find out what will be the flow depth and velocity. All right. This we have done for the both laminar and the turbulent cases. Okay. So, what we can do is we can apply these equations and determine what is the flow depth and velocity, and then we can check whether the flow is laminar or turbulent, and then we can modify our computations when we are applying these things. So, this is as far as the modeling of the overland flow is concerned. Whenever and when we are doing the modeling for the rainfall runoff process, all right, that is from the rainfall heatograph we want to find out the direct runoff hydrograph. All right. So, in that process we have to first calculate the effective rainfall heatograph. We have looked at that already in the last lecture. All right. Today we have looked at the first part of the rainfall runoff or the transformation of this effective rainfall heatograph into direct runoff hydrograph. How? By doing the modeling on the overland flow. Okay. Now, what happens after that is on that overland flow these small channels would form. All right, and after that this Q naught, that intensity will come into some bigger channels. Okay. So, what we will do next is we will do the channel flow modeling in order to develop the whole model for the rainfall runoff process. Okay. So, then we have the channel flow. Okay. So, if we look at the expression, not the expression, the schematic here, my sketching is not very good, but would like to try nonetheless. Okay. I am drawing a very simple case in which we are drawing a channel and this is your overland flow on its side. Okay. And there is some water in it. Okay. So, what we have is, let us say, this unit width of the overland flow, that is what we had considered. All right. Remember, this was L0. Okay. That is your overland flow, and what comes into this channel is your Q0. Okay. So, what you can do is you can divide your overland flow into different strips, all right, of different either the unit widths or any other widths. Okay. And then you can calculate this Q0, all right. The equations we have already seen. This Q0 will be coming into the channel, and then the channel, then the flow will be going into the topographic direction or the favorable slope. Okay. So, let us say in this case your flow direction is, let us say, this. Okay. So, you will have this Q's coming in here, all right, at different lengths, and then you have the depth of flow is y here in the channel and the velocity is v. Okay. So, now our objective is to determine what will be the flow depth and velocity in the channel given the discharge in this channel. Okay. How can we do that? How can we determine the flow depth and velocity in a channel? Well, we use the famous Mannix equation. All right. We would see that this problem will not be very straightforward. All right. It will involve a little mathematical jugglery. All right. So, let us look at that. First, define various variables involved. So, you have LC is the length of the channel. This is the length of the channel, and let us say that Q naught or Q0 is the discharge per unit width from the overland flow into the channel. Okay. So, that what will be the total Q in the channel? All right. The total Q in the channel will be Q0 multiplied by the total length of the channel, which is LC. Okay. So, it would be Q0 times LC. All right. let me move on. Then what we are doing is, our objective is to find y, that is the depth of flow, and the velocity, okay, at various points along LC. Along the channel length, we need an iterative solution of the Mannix equation. Okay. Well, what is the Mannix equation? You know that Q is equal to 1.49. We will do this for FPS system, which can be easily extended to the SI system. R 2 by 3 S half, this is S0 is equal to, let us say, S naught S0, and this is my equation number 5.6.12. Okay. Now, where R is the hydraulic depth, which is A by P, which will depend upon the shape of the channel. All right, as we are talking about the natural flow in the natural environment. All right, so it's not a very nice shape. Okay, it will not be rectangular or trapezoidal like we are used to, but it can be in any natural shape in which the both R and A and P will be function of the depth of flow. That is why this equation will be implicit in nature and it is non-linear. So, we will have to use some iterative technique. When we talk of solving an implicit non-linear equation, there is a very famous method which we can use or which is most popular or very efficient method, which is called the Newton-Raphson method. Okay. So, what we will do is, we will apply the Newton-Raphson method to solve for this equation. Okay. In the Newton-Raphson method, we need to formulate a function, all right, for which you have to find out the root. In this equation, the function will be the error. All right. What is the error? In any iterative process, you start with an initial guess, all right. Corresponding to that initial guess, you can calculate the error, all right, and then you try to minimize that error in the successive iterations. Okay. So, our error function is which we try to minimize. Let us call this f as a function of yj. Yj is the depth of flow which we are trying to find out. Okay, is equal to, let us say, qj. Qj is the value or the guess of your q at the end of a jth iteration minus q. This q we already know, we have already determined using the overland flow. Okay, and this q is an iterative q which we are guessing based upon this value of yj. Okay. So, in ideal conditions, your y should be such that your qj is equal to q, so that your error is 0. Okay. So, that is our objective, is to determine f of y using the Mannix equation. Okay. How do we do that? Well, the Newton-Raphson method, it involves these steps, where what you do is, you initially select an arbitrary value of your variable which you are trying to find out, yj. All right. Initially you get started, all right, and then once we know yj, all right, we can calculate qj from this equation, all right, from the Mannix equation. So, your second step is compute or estimate your qj using Mannix equation. Okay. Once we have calculated qj, the third step would be compute or estimate the error function. Okay. What is the error function? It is f of yj, which is nothing but qj you have just calculated, and value of q we already know from our overland flow. Okay. So, this will be able to give you the difference, which is the error. And then you just check for the convergence criteria. Okay. That is to say, you calculate the error at the end of the iteration. If the error is acceptable, you stop. If the error is not acceptable, you start iterating again. Okay. So, this is the step by step procedure of Newton-Raphson method, and what we will do is we will try to apply this in this particular case. Before we go to that, I would like to look at the basis of the Newton-Raphson method. Okay. I am sure all of you have seen what is the Newton-Raphson method, all right, how it is applied and how it is actually developed. All right. So, what I will do is I will first give you the equation, Newton-Raphson methods equation, and then we will see how it is actually derived on the basis on which is, or the concept on which it is based. All right. As you know, it gives you the guess for the next iteration j plus 1, all right, as what? As the value of the variable at the previous iteration y j minus the value of the function at that iteration divided by what? Divided by the derivative, the first derivative of that function at that iteration, all right, which is df over dy in this case, all right, at the jth iteration, and this is your 5, 6, 17. Okay. So, what I would like to do is I would like to derive this expression based on the concept of the Newton-Raphson method. The basis of the Newton-Raphson method is that it is, or the Newton-Raphson method, what does it do? It extrapolates the tangent. All right. You have a function, a nonlinear function, you have a starting point and you take a tangent on that point, all right, of the error function in this case, all right, at the current depth y j, or current root of your equation, to obtain the depth at the next iteration, which is y j plus 1, all right, for next iteration. Okay. So, if you look at it graphically, what it means is that we have depth y j, all right, and there is some function, nonlinear function f of y j. What is this f of y j? We have already defined, it is q j minus q, all right, in which q is a constant and q j depends upon the depth of flow y j, all right. So, we are guessing this depth of flow y j initially and then we are iterating until some convergence is reached. So, at any iteration we want to find out what is the next depth of flow or the next value of the root of this equation, all right. So, let us say that you have the error function is something like this, okay. Then let us say your initial guess is this, which is your y j, okay. Then you take the tangent on it, all right. What is the basis of the Newton-Raphson method? At the current point, you take the tangent, all right, and you see where it cuts the x axis, let us say that is where it cuts, and that is what will give you the next point. Okay. How does it come? Well, let us look at that. Okay. What we are doing is we are saying that the Newton-Raphson method extrapolates the tangent, all right, of the error. What is the equation of the tangent at that particular current point? Well, it is nothing but the first derivative, right. So, if you write the first derivative df over dy at your jth iteration, means at this point, this is your point on the curve and you want to write the first derivative equation of this line. Okay. What would that be? The first derivative of a line is nothing but y2 minus y1 over x2 minus x1, all right. So, what is the y2 minus y1? What is the value of your f of y at the second point and the first point? Well, it is 0 minus f at y j. Do you see that? All right. Y 2 minus y 1, that is the function value at the second point and the first point, divided by x 2 minus x 1, x is y here. So, you have y j plus 1 minus y j. All right. So, all you have done is you have taken the slope at the current point or at the current value of your root of the nonlinear equation. Okay. So, if you solve this equation, this will essentially give you the method, or the y j plus 1 is equal to y j minus f of y j over f prime of y j, okay, where f prime of y j is nothing but this quantity. Okay. This is your NR equation. Okay. So, you see that this Newton-Raphson method is based on a very simple concept, in which the next guess or the value of your y at the next iteration is calculated using or by drawing the tangent at the current point to the curve, and then finding out wherever it cuts your x axis. Okay. All right. So, with this basis, this is our equation. So, what we can do is we can start with any arbitrary value of y j, calculate your function and the derivative of the function, and that will give you the depth of flow at the next iteration, and we keep on doing it. Okay. However, we need to find out what is going to be this function and f prime of the function, okay, because the function which we are dealing with is extremely complicated. Okay. So, let us look at this function, which will be in the form of the Mannix equation. Okay. All right. So, we had said already that what is f of y j? What is our function? It is your q j minus q, okay, which is 1.49 over n r 2 by 3 s 1 half, all right, minus q, where capital Q is the discharge coming from the overland flow, which is constant, and we have calculated that. So, that is some number, let us say 23.4 meter cube per second, all right. That does not depend upon depth of flow. What depends is your gas. So, this quantity is equal to function of y j, right. Okay. So, what would then your df over dy at j be from this equation? All right. What you need to do is you need to differentiate this equation with respect to y, all right, and that will give you the f prime. So, if you did that, what you have is d over dy j of your q j. Okay. The derivative of this quantity with respect to y, the derivative of this quantity with respect to y will vanish, because this is a number. All right. So, all you have is this is a function of y. So, it will be dq j over dy j. Is it clear? All right. So, now q j is given by this expression 1.49 by n and so on, and that is where your r is a function of depth of flow. Okay. All right. So, if you did that, then you have, let me go back, this is actually your velocity. So, I think I need to multiply this by area somewhere, all right. So, that is going to be your area. So, in this equation your r is function of y, and also the area is your some function of y j. So, now you have a product of two things, or two functions which depend upon depth of flow. Okay. So, what will be dq over dy? This will be equal to d over dy of, let me write it down, 1.49 over n under root s, okay, and then you have a j r j to the power 2 by 3, right. All I have done is d over dy of q j, and for q j you have put this value here, that is your q j. Okay. Now, what would that be? Well, you can take the constants outside, it will be 1.49 slope is constant, it is not changing as a function of depth of flow. So, that comes out. N is the Mannix coefficient, that is also not changing. So, that also comes out. What remains is Aj Rj 2 by 3. All right. So, it is a product of two functions, you differentiate it with respect to y. Okay. So, let us do that. It will be 2 by 3, please follow it carefully, and if you cannot understand it, just try to do it independently. Okay. So, you have product of two functions, the first derivative would be first one multiplied by the derivative of the second. All right. So, we are differentiating the r term first. Okay. So, the differential of this quantity would be 2 by 3 r j to the power 2 by 3 minus 1, which is this, times dr by dj is also there. All right. And then you only have the a here. Okay. Then plus you would have r to the power 2 by 3 times dA over dy. Okay. See that carefully, you have Aj and Rj to the power 2 by 3, it is a product of two functions, and then you are just differentiating it. All right. So, let us simplify this then, let me move to the next page. It would be equal to 1.49 under root s 0 over n. All right. And then what you can do is you can take this thing outside, Aj Rj to the power 2 by 3 is common. What will remain inside is 2 over 3 r of your dr over dy plus 1 over a. All right. Because you have taken a and r outside, so you will have to divide by these things. You have dA over dy evaluated at j. Okay. And this is equal to your df over dy at the jth time step. Okay. Now, this whole expression, all right, this is function of the depth of flow and it is a complicated function. This is called the channel slope function. Okay. And we will come to that little later. All right. What is this quantity? This whole thing? This is nothing but Qj. Okay. So, then your equation for f prime is df over dy at the jth iteration is equal to what? Qj times your channel slope function, which is 2 over 3 r dr dy, okay, plus 1 over a dA dy at the jth iteration. Okay. So, now we can do what we can do is we can substitute this quantity in your Newton-Raphson method. Okay. We already have the function, now we have the derivative of the function. So, we can use the Newton-Raphson equation. All right. So, if you did that, you will have y at j plus 1 then is equal to what? Y at j minus function f y j, which is what we have defined as Qj minus Q. That is the function which is the error, divided by f prime. What is f prime? It is nothing but Qj, we have just derived it here, multiplied by the channel slope function, which is 2 by 3 r dr dy plus 1 over a of your dA dy evaluated at jth iteration. Okay. We can do some slight rearrangements here and simplify this to say that you have y at j plus 1 is equal to y at j minus, you divide the numerator and denominator by Qj, so that you would have 1 minus Q over Qj, this whole thing divided by 2 over 3 r dr dy plus 1 by a of your dA dy evaluated at the jth time step. So, this I am going to number as 5, 6, 18. Okay. So, you see that this is a complicated expression we have derived for finding out the depth of flow in the channel, all right, using Newton-Raphson method, all right, which is an iterative procedure. At each iteration, we need to compute this channel slope function, all right. This is a complicated expression we have said, and this is a function of what? This will depend upon the shape of the channel, because it involves what? The area of cross section and also the hydraulic depth. So, the hydraulic depth and the area of cross section will depend upon the shape, all right. The value of this channel slope functions are given in a table in the book, all right, for different shapes of the channel, all right. So, for different shapes of the channels, the channel slope function expression or the equation actually are available in standard tables. All right. And this is given in your Chow's book in this chapter 5. Okay. All right. So, once we have calculated this depth of flow, we can easily calculate the velocity of flow in the channel by applying the Mannix equation. All right. So, with that I think I would like to stop at this point of time, because I am at a good stopping point. So, what we have done today is we have looked at the modeling of the overland flow and the channel flow, and the objective is to find out both flow depth and velocity in the overland flow and in the channel flow, and in the process we have carried out the complete modeling of the rainfall runoff process. In tomorrow's class, what we would do is we would look at some another method of carrying out the rainfall runoff modeling, which is using the what is called the time area concept. All right, using the time area concept, that is how we can develop the isochrones in a catchment and how we can calculate the direct runoff hydrograph from a time area diagram. Okay, that will be one thing, and then we would look at an example of the channel slope function, not the channel slope function, the example of the application of the time area diagram. Once we have done that, we would also look at a few topographic characteristics of a catchment. Okay. So, these are the few things remaining in this chapter, and we would try to finish it tomorrow. Thank you.